So now let's start this topic about this polymers. So let's understand this monomers, polymers, monomer residues, functionalities, degree polymerization, and this PDI. Suppose if you take the example of this polymers, if we take example here, if we have here kind of the styrene example, if we have the styrene example, and if n number of these molecules polymerizes, what happens? There is, we have kind of this polymer. So here, this one is known as a monomer, and this is as the polymer. Here, in number of molecule of the styrene polymerizes and gives us the polymers. And here is the n number of the molecules of the polystyrene polymerizes here. So here, if you can say here is that there is kind of the polymers long chain of this polystyrene molecule. Now we understand about these monomers and these polymers. And other thing here is the monomers residue structure of the repeat unit. So here in the polymers, this is the repeat unit, right? So if you think about, so this is the repeat unit there. So we have this repeat unit. So here we have the repeat unit. So in folder. Well, so we have the repeat unit here, right? And here this repeat unit also called as the structural unit or the monomer residue. And we can take the other example. For example, maybe let me take the other example here. Suppose if we have here OH, we have the OH and we have C-double OC and R prime C-double OC. And it gets, so what happens? We have R O C-double O, R prime C-double O, we have OH and we have H2O. We have the n number of molecules. What happens here? We have this one is monomer. This is also the monomer here, and this is this polymer chain, and this is the n number of the molecules in that polymers. So this is the mono. So in particular, this example, we have only one kind of the monomer. However, in the second kind of example, we have two monomers. We have here two monomers. Here we have the only one monomer. So based on that, the number of the monomers, we can two kinds of the monomers. We can also have the classification based on this homopolymer and copolymer. So here this is called as the copolymer, and this is the example of the homopolymer. Okay, homopolymer and the copolymer. Now let's understand the functionality here. So now let's understand here this functionality. Okay, we can have the functionality here. In this particular in this particular monomers, we have here two OH group, and here the functionality means the number of the sites on which the polymerization reactions can happen. So in this particular monomers, we have this two OH group, and where the polymerization can happen from here and as. And that's why here the functionality of this monomer is 2. Similarly, here we have the diacid, and we have the two sides where the polymerization reactions can happen, right? So we have here two functionality. We have the function 1 and 2 functionality there. In the case of this styrene, we have a styrene here. Even though in this styrene we have functionality 1 and here's 2, because even though in this particular molecule there is the polymerization reactions happens from this side and this side, so this polystyrene styrene has functionality is equal to 2. This alcohol has functionality 2, and the diacid has the functionality of 2. So here the functionality is denoted with the small f, and based on the functionality, there are different kinds of the polymers chain can happen, the structure of the different polymer chain. Let's understand what kind of the polymer chain reactions happens. Okay, so suppose if you have this two and the three functionalities in the monomer, then in that case, they may be the linear or the branched or the cross-linked polymer reactions can happen. For example, if you have here if A is equal to 2, for example, you have OH, we have R, and you have OH. So in this case, there is the linear polymers chain forms. If you have this polymer functionality of the three, if we have this monomer which has three functionality, so in that case, for example, glycerol, if you take the example, if take the example OH, if take the example CH2OH, right? So here there are the three OH group, and because of that, there are the possibility of the formation of the polymers from here, here, and here, and therefore there is the formation of this branched polymers forms. So if you have this two functionality, in that case, you have the linear polymer. And if you have the three functionality, in that case, you will have the here branched polymers. You have this branched polymers, and here you have the linear polymer. That is based on the functionality, different functionality of the monomer, right? Okay. So we understand the monomers, polymers, and the repeat unit and the functionality. I will discuss this point, degree of polymerization and this PDI, when I will discuss about molecular weight distributions and determination of the molecular weight. So I will discuss this point in details when maybe in the fourth or the fifth class. Okay, so after the basic understanding about the polymers, monomers, we have the classifications. So if you just take the example of all the polymers are classified based on the 4 points. First classification is based on the origin of the polymers. Second is this kind of this polymer structure. For example, linear branch, some kind of structures, and then other one is the polymerization mechanism. Which kind of the mechanism that take place in the polymer formation? So that is the polymerization mechanism. And the fourth is the thermal behavior. How do polymers behaves when you heat or maybe you supply the thermal energy? So we have the 4 different parameters. So now let's take one by one. If we explain about this polymer that is based on the origin of the polymer, so we have these two kinds of the polymer. One is the natural polymer and the other is the synthetic polymers. So natural polymers means the polymers that can be available naturally is called this natural polymer. For example, if you think about the natural rubber, so you can extract the natural rubber from the tree, right? So that is the natural example of natural. If you think about the wool, that is the natural process, natural polymers. And if you and as the synthetic polymers, we synthesize polymer in the laboratory by the chemical reactions. So, for example, if you take this Teflon tape. So here the Teflon tape is the example of the synthetic polymers. If you think about the synthetic rubber, so these are the materials that is based on the origin of these polymers. And the second classification is based on this polymer structure. If you just classify all the polymers based on the structures, then we have the three different kinds of the structure of the polymers. One is the branched linear polymers. So now let's understand. So if you think about the linear polymers, we have this linear polymers. So linear polymers, or maybe the linear polymers maybe can be present either way in this coil form. So here, so these are the example of linear polymer. And the branched polymers. If you consider the example of this branched polymers, so we have the polymers there, and if you have some kind of this branching happen there, so this is the example of this branched polymers. We have the short branching. If you have the long chain length and you have the short branching there, so this is example of this branched polymer. And the cross linked polymers means you have this polymer there, if you have this polymer and you have such kind of this branch, so there is the cross link there, right? So this is the example of this cross linked polymers. So this is the example of cross link. So this is the example of the cross linked polymers. So we understand first one is the based on the origin of the polymers, that is the natural and the synthetic polymer. Second is the example based on the polymer structure. So based on the polymer structures, we have the linear polymer, we have the branched polymer, and we have the cross-linked polymers. Again, based on this, polymer structures, we can define all the polymers, three kinds of the three polymers. One is the based on the again the structures that polymers may be the crystalline polymers, amorphous polymers, and the semi-crystalline polymers. For example, in the crystalline polymers, so in crystalline polymers, as you studied solid state in class 12, if you have the crystalline materials, you have this position of atom in that crystal is fixed. That means orientations and position of atom is fixed in the crystalline structures. Maybe for take the example of FCC, BCC, right? Similarly, in the crystalline polymers, you have the chain of the polymers. You have the long chain of the polymers. So here, in the crystalline polymer, that means the position of the chain of the polymer is fixed. That means position of the chain is fixed, the orientation of polymers is fixed, and that is the example of the crystalline polymers. So in that case, we have this fixed orientation. So we have fixed position of chain of polymers, right? We have this fixed chain positions. We have fixed orientation orientation of chain, right? So that is the crystalline polymers. In amorphous polymers, we have this polymers chain, but their position is not the fixed position. There is some kind of a randomness in this chain of the polymers. Suppose you have the polymers, and there is some kind of the randomness in this chain position of the chain. So here, so in this case, in amorphous polymers, you have position position of chain is random. And because of the randomness in their position, the structures is amorphous kind of things. And other is the example of the semi-crystalline polymers. And there is the example of the semi-crystalline polymers. So in that kind of the polymers have this both of properties, crystalline and this amorphous structures as well. And we are going to learn and understand how these different structure of the polymers affects the glass transition temperature and the melting point of these polymers. Polymers, structure of these polymers. Okay, so in later on we will go and understand how. So if we have the how it temperature and how this material is behaves, maybe if you have kind of things, you have the kind of things, so how these different material or different structures of the polymers affects their glass transition temperatures, and how you define a glass transition temperature, and how that glass transition temperature affects the mechanical properties from the glassy state to the rubbery state. Also, we will studied this phenomenon in second class when I talk about the glass transition temperature of the polymer, and the other one is the classification that is based on these polymer structures. So we had just classification of the polymers based on the structures, maybe linear branched and is cross-linked. Second is the based on the crystal crystallity of the polymers, may be the crystallines, amorphous, and semi-crystalline polymers. And third is based on the polymer structure, that is the homopolymer and the copolymers. So we are going to learn this kind of the polymers. So in homopolymers, as I took example of polystyrene, so we have polystyrene, and if n number of molecules polymerizes, and that gives this polymers. So here n number of the monomer polymerizes and gives the polystyrene. So here it has the only one kind of the repeat unit in that polymer, and that's why this is called the homopolymer. This, if you take example A, so this is kind of AN. So this, okay, let me write. So this is kind of the polymers where you have A. So you have the only the one kind of the repeat unit, that polymer is called the homopolymer. What about the copolymer? Suppose you have the polymer here. Suppose you have the polymer here. If you have this polymer CH, PH, you have two kind of the monomer. And if you have CH, CN, and here CH2, so it will form kind of the copolymer. So here you have CH CH2 pH. So we have polymers. So this is M and N. So this is N, and here we have the Cn, we have the C2. So we will have the M. So so take the example here. We have the here two kind of the monomer. One is styrene kind of here. We have this phenyl group here, and we have here the cyano group here. So we have these two kind of the monomer. And if that monomers reacts together, polymerizes, so we have this kind of the polymers where we have this is one repeat unit and this is the second repeat unit, right? So this is called as the copolymers, copolymer, where you have two kind of the monomer. So the polymers which has these two kind of the monomer is called copolymer, and the monomer which has the one kind of the monomer is called homopolymer. Okay, so we understand this classification, that is the homopolymer and the copolymer. Again, based on the so we can classify these copolymers based on the structure and the repetition of the monomers in that repeat unit. So here that is what we can take it as the simplest example is that's based on the simplest example. So we have A and we have M, B, and you have A repeat unit, and we have here the repeat unit, right? So this is kind of the copolymer. So based on the position of the repeat unit in the copolymer, we have the four different kind of the copolymer. That is random copolymers, alternate copolymers, block polymer, and the graft copolymer. So in the random copolymers, what happens? So in the, for example, let's take the example of AAA. So in the random copolymers, we have, suppose we have A plus MB. So we have A, B, 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 A, B, B, A. So there is the randomness in that, the repetition of the monomer in that polymer. And that's why this is called this random copolymer. In the alternate copolymers, we have B, A, B, A, B, A, B, A, B, kind of the repetition of the monomer in that polymers. So that is the repeating after again and again in particular interval is called the alternate copolymers. And in the block polymers, and if you think about the block polymers, so here the block polymers is kind of, you have this two kind of the block. That is polymers part of A monomer and the polymer part of the B polymer, and this is the example of the block polymers. For example, if you have here kind of A, 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 B, and B, 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 maybe A, B, 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 B. So you have here this one, if you think about, so you have here block, you have the kind of the block. So you have block of A, block of B, block of A, and block of B. And based on that block of those monomers, you have the different block copolymers. And this kind of the arrangement of the monomer in the polymer is called this block kind of those polymers. And we have the other example of the graft polymers here is that, for example, let me wipe it out. Let me make some space there so that I can show it here as an example of graft polymers. Okay, so in the graft polymers, Just wait a second. Wait a second. I'm making some space there. So in the graph polymers, we have for example, we have a kind of this polymer. We have homopolymer of A, right? And we somehow we and again we have this some kind of B kind of this polymer there is B there. So this is kind of example is the graph polymers where you have this is the homopolymer of A, and you have the other homopolymer, and that forms the polymers there, and this is called as the graph polymers. Okay, so we understand the classification of the polymer that is based on the structures of the polymers, and we have to understand the homopolymer and the copolymer, and the copolymer has four different kinds of the polymer, that is randoms copolymers, alternate copolymers, block polymers, and the graft copolymers. Now, again, we can classify polymers based on the structure of the polymers. And that is based on the structure of the polymers, we have the fibers, plastic, and elastomers. Let's understand how we can define this that kind of the polymers. So here we have the fibers kind of the polymers. And when we think about the fibers, so fibers have the certain properties, and that certain properties, for example, so the fibers polymers has is kind of the linear polymers. Okay, so fibers is kind of the linear polymers. You have the kind of those linear polymers. Second, because of the linear kind of the polymer structures, it has the high intermolecular interactions, right? So so it has linear structures and it has a very high intermolecular interactions. For example, here the interactions may be kind of the hydrogen bonding. It may be kind of the van der Waals interactions, and maybe there is the dipole dipole interactions. So here, interactions may be the hydrogen bonding, van der Waals, maybe the dipole interactions among those linear polymers. So we have the such kind of the interactions may be present there, maybe such kind of the interactions there. And because of this strong interactions among the chain, this kind of the fibers polymers has very, so it has the properties like it like because of the linears and the strong interactions, it has a very high modulus, and it has very high tensile strength, right? And very low elongation, maybe a strain. So these are the properties of these fibers. And what about those elastomers? And if you think about the elastomers, so here elastomers has the distinct properties. For example, here the elastomers has the properties. For example, here there is no fixed orientation, so there is irregular irregular interactions or irregular chain of polymers, or maybe irregular structure of the polymers, and weak intermolecular intermolecular interactions. So in elastomers, there is irregular orientations of the structure of this chain of the polymer, and there is weak intermolecular interactions. So because of the weak intermolecular interactions, this kind of the polymers has very low modulus, and it has very low tensile strength and high very high strength. So this kind of this elastomers maybe can have the elongations maybe close to maybe the 1000%. Maybe in some kind of the elastomers has the elongation that is close to the thousands percent increase in elongations. So we have understanding about those fibers and the elastomers. What about the plastics? Plastic has intermediate properties between fibers and the elastomers. And based on that intermediate properties, it has the mixed mechanical properties. So now let's understand how these fibers, plastics, and elastomers kind of the materials has different properties in terms of the mechanical properties of the polymers. So in this particular graph, we have two axes. One is here, this is the tensile strength, and that is tensile strength, and or maybe you can say stress. And this is example of the strength. And here the unit of this tensile strength is the force per unit area. And here this is the unitless. Then this is the delta x upon x. So this is the unitless. And if you just see the variation of the strain with the stress, so we have the very important kind of the observations here. So for the elastomers, we have, see, if you think about the kind of the change in the elastomers. So in elastomers, so here, even though at very low stress or the tensile strength, there is the huge change in the strain, or maybe the change in the change in the length of this polymers. However, so in elastomers, even though you apply the very less strain or the pressure, that material gets deformed at a very large extent. However, if you apply the same kind of the stress there at the fibers, so because of the very high, so here, so this is the fibers this is for fibers. So here in this case, even though you have the very high tensile strength, but even though at very high strength, you have the very low or negligible strength. That means if you apply very high pressure on that polymers, and even though that at very high pressure, there is very negligible change in their size of the polymers, or maybe the elongations. However, the plastics has this intermediate properties. For example, here the plastic shows here up to here is shows that there is the very high kind of the tensile strength, and after that there is showing the properties of the elastomers. Even though it's the minus change at the pressure, there is a huge change in the strength. And the plastic are also two kinds of if we have the flexible plastics, in that case there is the initial properties kind of the fibers, and there is the furthest properties of this elastomers. However, in the rigid plastic, that has similar properties as the fiber, and which has the very high tensile strength as compared to the strength. So we will have this kind of the discussions about this mechanical properties of the polymers as later on this class in this topic. And after that, we have classification of the polymers based on this polymerization mechanism. We have these two kinds of this mechanism, that is the condensation polymerization, and the second is the addition polymerization reactions. In condensation polymerization reactions, for example, as we had example about this one is we have this one, we have OH, and we have n number of molecules. And if you have the n number of molecules of the diacid, and then we will have here, we have the polymerizations. Sorry, this one is kind of, we have S2. So here, alcoholic group here that is condensed with the dicarboxylic. So here the carboxylic group. And because of the mechanism associated with here is, for example, you have ROH, and you have OLC, you have, so let's just take the example of, if you have the alcohol and if you have the acid. So here, it attacks there, and there is, it comes back, and then the remove of this one, and there is the formation of R prime O R2. So and in this case there is the release of the small molecules, that is the water, and because of this we classify this kind of the reaction is the condensation reactions, where there is the small molecules as a byproduct comes out. So based on the mechanism of the polymerizations, we can classify this one is the condensation polymerization reactions. And if we classify it, and in other one is we have this addition polymerization reactions, where we take to the example, okay, we have a styrene, and if that styrene gets polymerizes, we have PHCH2. Okay, and so this is the example of the addition polymerization reactions, because one monomer gets added to the other polymers, and there is the formation of the polymers. So in the additional polymerization, there is no such kind of this byproducts comes out. However, in the condensation polymerization, there is the small molecules, maybe the water, maybe the ROH, small molecules, comes out as a byproduct in the condensation polymerizations. So that is the difference of the additional polymerization and condensation polymerization. And based on that, we have two kinds of polymers, and that is the, and we understood this one. Okay, so we have another classification of the polymers, and that is the based on the thermomechanical properties. That means the properties of this polymers change with the properties of mechanical properties change the with the change in the thermal energy. And we have two kinds of the polymers, and that is the thermoplastics and thermosets. Let's understand what are these polymers. So thermoplastics polymers is kind of the polymers in which if you apply or supply the heat, what happens? So that undergoes in the cyclic process of hard materials to the soft material. So suppose you have this polymers, which is the hard material there, and if you apply heat there, if you add heat like this, so that becomes soft. And again, if you if you cool this material, so this is the heating minus delta H means delta means there is the cooling process, and the plus delta means there's the heating process. So if you have the material polymers material, and if you heat that material, so that becomes soft. And once if you cool that materials, that becomes again hard materials. So this kind of the cyclic process can happen multiple times without breaking off these polymers materials. So this is the beauty of the thermoplastics. However, thermosets materials cannot go in the cyclic process of the hard and the soft materials. In the thermosets, what happens if you apply or just heat, oh, if you heat it, if you heat the thermosets materials, what happens? They maybe so that materials undergo, so that materials undergoes chemical reactions, maybe I should write clearly, chemical reactions. And that reactions is example or kind of the cross linking. So initially you have this kind of the materials there. So if you have some such kind of the materials, and if you apply the heat there, so that undergo in this cross linking in this chain of the polymers, and because of this cross linking process and chemical reactions happens, the reversible process is not happens. So this is kind of hard and soft kind of materials that, and so that will not happen in the thermosets kind of the polymers. This is only one way of the transformations if you heat that materials. So that is the key difference in the thermoplastics and the thermosets. And now let's understand how the mechanical properties change, or the nature of the materials change if we supply some thermal energy there. And this is very important observation about mechanical properties. So, so if we measure modulus, Young's modulus, mechanical properties of the materials at a different temperature, so we will have the different kinds of the observations. So initially, if we have the very low temperature, in that case, both materials, thermosets and thermoplastics materials, present as a glassy state. at a very low temperature. In that case, we have this modulus, that is so that the Young modulus is the kind of the tensile strength by the tensile strength. So in that case, the Young modulus is very, very high for thermoplastic and thermoset materials as well. And once we increase temperature, what happens? So there is sharp change in the Young modulus there, and that becomes the rubbery kind of structure where they kind of the material. So once we have what earlier we have the glassy kind of materials, and once we supply the heat there, so there is sharp change in the mechanical properties, Young modulus, and we will have the decrease in the Young modulus there. So here, in this particular range of the temperature, we will have glass transition temperature, glass transition temperature, because the materials, polymers, is transformed from glassy states to the rubbery state, and temperature at which that transformation happens is called the glass transition temperature. And after that, we have the rubbery kind of structures, and we have this plateau of the CM modulus. And for those at very high temperatures, again, these rubbery materials gets in the viscous kind of materials, and that is a flow kind of viscous liquid. And in that case, we have very, very low Young modulus, right? So this kind of the behavior is for the thermoplastics. And this kind of the observations can be reversible. So here, so these properties can be reversible. So this can go this side, forward, and this backward process as well. If we increase temperature, so that transforms from this glassy state to the rubbery state to this fluid state of these materials. And we cool down that material, then we from the flow to the rubbery and the glassy state. But in the case of the thermosets polymers, we have the different observation. And this observations is about, so here, observations about this one is that in this case, in the case of the thermosets of the material, you have the glassy state, and this is the rubbery state, right? So we have rubbery state of the polymer. So you have that this one is a glassy state and this is the rubbery state, and so there's a very low change in this Young modulus. So here, if you think about degree of change of the Young modulus in the thermoplastics and the thermosets, there's a huge difference. In the thermosets, there's a minor change in this modulus. However, even in the thermoplastic, there's a huge change from the glassy stage to the rubbery stage. Why? Now the questions you might have that why there is so much difference in these mechanical properties. So as I told you that thermoplastics is kind of the linear kind of the materials, and it has so if you apply some temperature, so there is easily deformations can happen there. However, in the case of the thermosets, if you increase temperature, so once you have some linear and once you increase temperatures, so there is the cross linking happens. And because of the cross-linking, this material has very high tensile as Young modulus. So even though at increased temperatures, even in the rubbery state, this state has the high modulus as compared to the rubbery state of this thermoplastics, because it has the simple kind of the structures, and it can easily slides and deformed at the high temperature. We can understand this one thermoplastic with the example like as we all have candle right in our home, and candle wax is kind of the thermoplastics, because if you heat candle wax, what happens, that becomes very soft kind of materials, right? So you have soft material, so you can make some kind of structures, and if you cool down, that becomes solid kind of the structure, that particular structure. So you can do this kind of the conversation from soft to hard, hard to soft many times. And this is the example of the thermoplastics. However, when thermoset is difficult, we have the many materials. For example, we have the chair in our home. You cannot make the hard plastics or plastics and cannot make do again. So they are one types of the plastics. And this is example of the thermosets of the materials. So we have done with the classification of the polymers, and these are the very important parameters. It, we parameters we understand about the thermomechanical properties of these polymers, of the thermoplastics and thermosets. So this classification will help us to understand their behaviors, and so we can develop this kind of the polymers based on the different techniques. Maybe we can use bulk polymerization, emulsion polymerizations, and maybe suspension polymerization, solution polymerization, or maybe we can use the living radical polymerizations mechanism. So once we have the overall understanding about the kind of the polymers, their properties, we can study some more details about their thermodynamics. We can understand their chemistry and their properties. Okay, so so now we have left with the nomenclatures, and it is better to cover nomenclature in the next class.